We are here. There should still be some unsolved math problems out there.
Oh, this is
a calculation problem? It looks like a power of 2, but the 3 is written on the upper left instead of the upper right.
I see, so that's what it means.
Huh? What do you mean?
This is a kind of operation called tetration.
What's tetration?
Very well, I'll explain it step by step.
Please do.
To prepare for understanding tetration, let's remember that multiplication is repeated addition. For example, 2 times 3, or equivalently 3 times 2, can be expressed as 2 plus 2 plus 2. So the answer is 6.
We learned it in elementary school.
Furthermore, repeated multiplication is called exponentiation.
2 to the power of 3 means 2 times 2 times 2, right? So the answer is 8.
That's correct. Now then, let's calculate a tetration.
This is the one that appeared as a problem earlier.
Here, we'll read this as the third tetration of 2.
The third tetration of 2. I wonder how we calculate it. Repeated addition is multiplication, and repeated multiplication is exponentiation. So maybe repeated exponentiation is tetration? Here, we're repeating exponentiation using 3 2's.
You're sharp today, Zundamon. Yes, this is the third tetration of 2. In other words, 2 to the power of 2 to the power of 2.
That sounds kind of amazing.
Here we calculate exponentiation from the upper right. Well, in this example, calculating from the lower left happens to give the same result, but let's put that aside for now. First, if we calculate this part, 2 squared becomes 4. Therefore, we just need to calculate 2 to the power of 4.
2 to the power of 4 means multiplying 2 4 times. So the answer is 16.
Exactly. But the true power of tetration is much more than this. Let's calculate another example. So then what value do you think the second tetration of 4 will have?
The second tetration of 4 means lining up 2 4's and repeating exponentiation. Even though we say repeat, there are only 2 4's, so we just need to calculate 4 to the power of 4. That means we just multiply 4 4 times.
Yes, so the answer is 256.
You are quick at calculating.
Up to this point, the results of tetration were within a manageable range. But the third tetration of 4 will be something incredible.
Really? It just changed from 2 to 3, so I don't think it changes that much. Well, let's calculate it for now. The third tetration of 4 means lining up 3 4's and repeating exponentiation. Since exponentiation is calculated from the upper right, we should first calculate this 4 to the power of 4.
We calculated 4 to the power of 4 earlier.
Ah, you're right. 4 to the power of 4 was 256. That means we end up calculating 4 to the power of 256. Wait, 4 to the power of 256 means the product of 256 4's, right? This has gotten really crazy.
At least now we understand that the third tetration of 4 is insane.
Even though it just changed from 2 to 3, the value suddenly becomes unbelievably huge. Tetration is scary.
Now you see how terrifying it is, don't you? Actually, there's a more general concept that includes tetration called hyperoperations.
What's hyperoperations?
Very well. I'll explain it step by step.
Please do.
For simplicity, let's assume that a and b are non-negative integers. We take addition as the most basic operation, and by repeating it, we define new operations one after another. First, by repeating addition, we can define multiplication.
A times b means the sum of b copies of a.
Next, by repeating multiplication, we can define exponentiation.
A to the power of b means the product of b copies of a.
And by repeating exponentiation, we can define tetration.
The bth tetration of a means repeating exponentiation using b copies of a.
In this way, we obtain a concept that generalizes operations like addition and multiplication. That concept is called hyperoperations. Here, let's represent hyperoperations using a capital H.
The first hyperoperation is addition. The second hyperoperation is multiplication. The third is exponentiation. And the fourth is tetration.
Exactly. And since each next operation is defined by repeating the previous one, hyperoperations can be defined infinitely beyond that.
So addition and multiplication were part of hyperoperations all along.
You can think of it that way. Zundamon, be careful, a problem is coming.
What? Whoa, this is... Huh? It doesn't look any different from before.
Look closely, Zundamon. The zeroth hyperoperation has been added.
Wait, the zeroth hyperoperation? Hyperoperations start with addition, so there shouldn't be any zeroth hyperoperation.
It's understandable that you're confused. Here, it's saying that there is a hyperoperation before addition. In other words, an operation even more basic than addition. Let's organize the situation.
I'm counting on you as always.
The idea is simple. We just need to think in the reverse direction from before. First, tetration is repeated exponentiation. Then, what is exponentiation? Exponentiation is repeated multiplication. Then what is multiplication? Multiplication is defined as repeated addition. Now this is where the real problem begins. Each operation is defined as a repetition of the previous operation. That means even addition, which should be the most basic operation, might actually be a repetition of some other operation. For now, let's denote that operation by circle.
This is kind of interesting.
A plus B means applying circle to B copies of A, so we just need to find out what that circle is.
So it seems we should investigate what kind of expression A circle B is.
Now you can see what needs to be done.
Okay, to put the problem in one sentence, A plus B means applying circle to B copies of A. Let's figure out what that circle is.
Now consider how A circle B can be expressed as a formula.
Isn't this difficult?
It's natural to feel that way. In fact, as it is now, this is impossible.
What?
Because if we consider the case where B is 1, the left-hand side becomes A plus 1. On the right-hand side, A appears B times, which is just once, so it becomes simply A.
Oh my. If we subtract A from both sides, we get 1 equals 0, which is a contradiction.
Yes, which means we're overlooking something.
What are we missing?
Well, don't rush just yet. A to the power of B was the multiplication of B copies of A. Then what is multiplication? A times B means the addition of B copies of A. Here, let's try a slightly different interpretation here. To multiply a number by B means to perform the addition of B numbers. In other words, the operation times B can be broken down into the addition of B numbers.
I see.
Then what about addition? To add B to a number means to perform the circle operation on B numbers. So the operation plus B can be broken down into something applied to B numbers.
Plus B gets broken down into something. Could that something be 1? Plus B means adding B copies of 1.
You're really sharp today, Zundamon. But unfortunately, various problems arise here.
What?
First, there is the issue of whether this circle can be defined without contradiction. But even if we set that aside for now, the result of this addition becomes B. In other words, A disappears somewhere.
Ah, you're right. The A in A plus B has disappeared somewhere. What on earth is going on? If we just add A, the problem would be solved, but we can't just do that.
That's a wonderful idea.
Really?
Here, we start from A and perform the operation of adding 1 exactly B times. This certainly matches A plus B.
Yes, that's right.
So to correspond to the A on the far right, let's also add an A to the upper expression. You might feel it's strange that only the far right is A in the lower expression. But in fact, to properly define the operation circle, this turns out to be a convenient form. For now, you should be convinced if we keep going.
Please go ahead.
By the way, if we consider the case B equals 0, we get the equation A plus 0 equals A. That's because starting from A and performing the operation of adding 1, 0 times. In other words, if we do nothing, only A remains as it is.
That's true.
By the way, just as A is the starting point in the addition A plus B, we can think of 0 as the starting point in the multiplication A times B.
So we start from 0 and perform the operation of adding A, B times.
That's how it works. For this as well, if we consider B equals 0, we get the equation A times 0 equals 0.
If we start from 0 and do nothing, only 0 remains.
Furthermore, we can think of 1 as the starting point for a to the power of b.
Starting from 1 and performing the operation of multiplying by a b times. Yes, that does calculate a to the power of b.
Likewise, if we consider b equals 0, only 1 remains, giving the equation a to the power of 0 equals 1. Here, we assume that a is not 0. This can be considered one of the reasons why we define the 0th power as 1.
Wow, so that's how it works.
Now let's think about the true nature of the operation circle. When we calculate a plus b, we start from a and perform the operation of adding 1 b times. Or, starting from a, we perform the operation a circle b times. So here, the operation a circle corresponds to the operation 1 plus. By the way, although I haven't explained this properly until now, we consider the operation circle to be right associative. That is, we calculate starting from the rightmost circle.
I see. The true nature of circle is becoming clear. A circle means adding 1, which means that if you apply a circle to 0, it becomes 1. Apply it to 1 and it becomes 2. Apply it to 2 and it becomes 3. In general, if you apply a circle to b, it becomes b plus 1.
Excellent! At last, we've uncovered the true nature of a circle b.
A circle b means b plus 1. It's kind of a strange operation. It's asymmetric with respect to a and b, and more than that, a is completely ignored.
This is an unexpected result.
Circle was supposed to be an operation more basic than addition, but here plus is being used to define circle.
Some of you may indeed feel that the order of definitions is strange. In that case, you can think of a circle b not as addition, but as representing the next number after b.
Now that you mention it, since we assumed b is a non-negative integer, b plus 1 really is the next number after b.
Addition, multiplication, exponentiation. There is a mysterious world surrounding these familiar operations. After exponentiation comes tetration, and beyond that, hyperoperations exist infinitely. All hyperoperations are defined based on the 0th hyperoperation. That is, the operation of adding 1, or in other words, moving to the next number, is the beginning of everything.
Now I get it. Thanks for watching.
If you'd like to support this channel, consider becoming a member. In this video, we talk about the purpose of our membership. Check it out if you're interested. Well then, take care everyone.
See you later.